Let's look at factoring difference of perfect squares. Now, we kind of saw this when we were multiplying our binomials when we had, remember we called them a conjugate pair. The binomials were exactly the same, but one was a plus, one was a minus, and when you FOILed it out, ax times ax is your a squared x squared. Ax times the minus c, that's your minus acx. C times ax, there's the positive, and c times a minus c is a minus c squared. That these two terms were opposites of each other, and they canceled out, giving us this two-term polynomial. All right. Now, because this is binomial, and we factor things into a binomial, these difference of perfect squares like to hide in other polynomial steps. So if we start factoring here, I have x squared minus 25. Perfect square, there's the difference. We're subtracting. Take the square root of each one. X and 25, 1 plus, 1 minus. X squared minus 64. Perfect square, we're subtracting. X, 8. X plus 8, x minus 8. Now be careful here, because even though 9x squared is a perfect square, 36 is a perfect square, we don't want to go 3x and 6 and go 3x plus 6, 3x minus 6, because your binomials would have GCFs in them. So we want to take out the GCF of 9 first, and it starts as a difference of perfect squares. It will still finish as a difference of perfect squares in here. So square root of x squared, x, square root of 4, 2, x plus 2, x minus 2. Now, from our perfect square trinomials, remember we said any variable to an even power is a perfect square. So 16 is a perfect square, x to the fourth is a perfect square, 81 is a perfect square. We're subtracting. Take the square root of each one. Square root of 16 is 4. Square root of x to the fourth is x squared. You just divide the power by the root, 2. Square root of 81 is 9. So 4x squared plus 9, 4x squared. Wait a minute. This is one of the reasons why we like to write the minus 1 last, is because this is the last thing I'm looking at, and I'm going, wait, 4 is a perfect square, x squared is a perfect square, 9 is a perfect square, and I'm subtracting. Here is a difference of perfect squares binomial hiding within my first factoring process. So we can factor that down to 2x plus 3, 2x minus 3. 4x squared plus 9, no factoring. It's a plus, not a minus. So x squared plus 4, because it's a plus, you can't factor it. It's prime. 12x squared minus 75. Wait a minute. These aren't difference of perfect squares, but wait a minute. There's a GCF of a 3. Let's take out the 3 first. You have 4x squared minus 25 in the parentheses. This is a difference of perfect squares. So we'll put the 3 on the outside. We'll have a 2x plus 5 and a 2x minus 5. Now, this one's kind of interesting because most authors will tell you, oh, your first term has to be a positive. So take out the negative 1. We're going to look at another approach to that. So I have negative 1, then 36x squared, perfect square, minus 25y squared, another perfect square. Take the square root, 6x, 5y, 1 plus, 1 minus. Keep the negative 1 as the GCF out in front. Or, why not just put the 25y squared first and put the negative 36x squared, treat it like a minus, and put it second? That's a difference of perfect squares. 5y plus 6x, 5y minus 6x. This answer here is the same as this answer right there. Oh, we got all kinds of even powers here. 108 to the 4th, c to the 6th, minus 121, x to the 8th, y squared. Difference of perfect squares. Square root of 100 is 10. Square root of a to the 4th, a squared. Square root of a to the 6th, c cubed. Just divide the powers by 2. Square root of 121 is 11. Square root of x to the 4th is x to the 8th is x to the 4th. Set it backwards there. And the square root of y squared is y. So all even powers on your variables are perfect squares. So 10 a squared c cubed, 10a squared c cubed, 1 plus 11x to the 4th y to the 1st, 1 minus 11x to the 4th y to the 1st. And there's our difference of perfect squares.